So now we will start an important application of image processing, and the difficult one. It's more difficult than its importance because right now or today the image sizes are quite large. The image resolution has extended beyond human interpretation limits. So sizing or resizing, downsampling, upsampling, etc. of images are not a critical issue anymore. The bandwidth is a lot. The image sizes are great, and regardless of how accurate or properly you make the sampling, downsampling, it more or less works. Okay, so it's not very important nowadays, but sampling and downsampling is still a critical issue in communication systems because of the bandwidth limitations in satellite communications, for instance, or in whatever we may have. And okay, the bandwidth is getting larger, but the image sizes are also getting larger. So to perform accurately the downsampling or resampling is still an issue that must be done. Unfortunately, it's difficult to do so because in digital signal processing courses from those, you may remember how difficult it was to find a relation between the Fourier transforms of subsampled, downsampled, upsampled, etc. signals. It was very difficult. And now we will extend it to 2 dimensions where periodic sampling requires periodicity within a matrix form. So it will be 2-dimensional periodicity in the lattice form, and we will do sampling or downsampling or upsampling on those lattice structures. It will be indefinitely more difficult. I will guarantee you this one. And it's fun to mess around with the mathematics of that, but it's not easy. I have to warn you about that. So we will start by remembering first what sampling was, and then we will see how to extend it to multiple dimensions, particularly 2 dimensions. If it becomes 3 dimensions, it becomes a multiple more difficult. But that's also an issue, by the way, 3-dimensional sampling or subsampling, because videos are 3-dimensional entities. There's a horizontal and vertical space direction as well as a temporal direction, which makes a volumetric 3-dimensional data. And subsampling of it is an interesting thing. For instance, in regular video systems, it is temporally subsampled in a hexagonal manner. What do we mean by that? We mean that conventional, classical, old school TV signals I'm talking about. First, the even signals arrive, and then the odd signals or odd lines arrive, and then the even lines arrive, and then the odd lines arrive in an interleaved manner. And when you visualize it in a temporal video streaming, odd, even interleaving gives us an impression that the resolution is essentially larger. So that is also a beginning of non-rectangular sampling and downsampling, because it's in the form of hexagonal. In 2 dimensions, we will also deal a lot with those non-rectangular or non-square sampling and subsampling, because they are more efficient, but mathematically they are more difficult. So now let's remember what sampling was. Sampling was a process starting from a continuous time signal, something like this, maybe. Let's call this signal x sub c of t. Sub c corresponds to continuous time. And then we were multiplying this with an impulse train. That's the classical way of doing it. And when we multiply with an impulse train, we were obtaining these scaled impulses after the multiplication. That was a first step for sampling from continuous time. And of course, this impulse train has a period. Let's say that the period is capital T. So on the continuous time axis, it will be a space axis in images or in 2 dimensions. We will have a different periodicity. It will not be just capital T, but it will contain a matrix, a 2 by 2 matrix, as you may already start guessing. So there's always an underlying xc of t, and after multiplying with an impulse train, it will be x sub s of t. Sub s corresponds to sampled version, but it's still on the time axis. So the axis here is still t. But afterwards, these samples will be stacked along an integer axis, an n axis, and the value at 0 will be the value at 0 in n, but the value of at capital T, that impulse magnitude, will be appearing as a number in 1. And 2t will be 2, 3t will be 3 along the n axis, where we are going to denote everything as x of n on the axis of n. Which will be like the value at 0 is here, the value at 1 is here, the value at 2 is here, at 3 is here, at 4 it's here, 5 will be like this, and 6 maybe will be like this. So the axis values will be 0, 1, 2, 3, 4, 5, 6. So x of n will look like this. Now, a critical observation that we make is that after sampling, we forget what capital T was. We don't remember it anymore. This is x of n, and it is irrelevant or independent from capital T, but it is related to capital T if you want to relate everything to x sub c of t. So this x of n could be obtained from a narrower version of this xc of t, which is so the underlying continuous time signal can be a higher frequency signal. Everything may be narrower, but the sampling period is also narrower. If you take it like that, a narrower signal and shorter capital T, it may still give you the same x of n. Or vice versa, this can be a wider version of this x sub c of t, which is a lower frequency signal. And this capital T can be taken wider capital T intervals for sampling, and it may still give you the same x of n. So you don't really remember or know what the original signal was, as long as you don't know what capital T is. But by the knowledge of capital T and by the knowledge of x of n, you can always go back to x sub c of t. So how are we going to relate all these things in the Fourier domain now? We have 3 different signals, x sub c of t, x sub s of t, and x of n. 2 of them are continuous time, 1 of them is a discrete time signal, and they have their corresponding Fourier transform. X sub c of t will have a continuous time Fourier transform. X sub s of t will also have a continuous time Fourier transform. X of n will have a discrete time Fourier transform. Look at those Fourier transforms. They are all over the so-called omega axis. How can we find the formula to relate everything in the Fourier domain? How can we relate these 3 signals in the Fourier domain? That's where we have to resolve first. And for that, of course, we have to find first the relation between x sub c, x sub s, and x of n in the time domain. We can write that x s of t is equal to xc of t times an impulse train. We can give a name to that impulse train. Let's call it S of t, a sampling impulse train. And it has a definition. It's a multiplication that I'm writing here. The definition of S of t is, it's an impulse train, as I say, consisting of infinitely many impulses separated by capital T. So it is a summation, an infinite summation from minus infinity to infinity, delta T minus n times capital T. This is the impulse train. So when I multiply x sub c of t with this impulse train, I will get x sub s of t. Simple. And we are automatically assuming that the values of these multiplication values of the impulses can be measured, evaluated, and this x of n at the right-hand side will have those values. For instance, if the value here is a, and this is b, and this is c, the value we read as a, b, and c here. Of course, since it's a multiplication in time domain, the Fourier transform relation between x sub c and x sub s will be a convolution of the Fourier transform of xc of t and s of t, the Fourier transforms of these two things. What I'm saying is x sub s of omega will be equal to the convolution of x sub c of omega and s of omega. And for that, we need to determine this, what is s of omega. It's the Fourier transform of s of t, and there's a definition to that. You may or may not remember it, and if you don't remember, you have to take it as granted, or you have to check your knowledges from signals and systems. If there is an impulse train, its Fourier transform is also an impulse train. And that's an interesting thing, because every impulse in the train will actually contribute as complex exponentials, sinusoids. So we have infinitely many sinusoids. There is a DC part corresponding to the impulse at 0, and all the others are sinusoids. If you sum up all those infinitely many sinusoids, an infinite summation of complex sinusoids will give you an infinite summation of impulses. That's interesting, isn't it? So you may think of it as trying to write S of t, which is a periodic signal, in terms of the Fourier series coefficients. And the Fourier series coefficients of that periodic signal, the impulse train, are always the same. It's always 1 over capital T. All the Fourier series coefficients are 1 over capital T. So I will multiply the Fourier series coefficients with the corresponding harmonic, and those harmonics will add up to an impulse or a set of impulses. That's an interesting observation. I was quite surprised when I first saw it. And many students, many of you guys may not even understand what I'm talking about. But it's interesting that if you sum up infinitely many sinusoids, you come up with infinitely many impulses, and that's interesting. And the Fourier transform is an impulse train, which is 2 pi over capital T. That 2 pi comes from converting everything into an impulse of harmonics in the Fourier domain. You may also want to check your notes from signals and systems. Let's say k from minus infinity to infinity, an infinite summation of impulses on the omega axis. But how much are they separated? They are separated according to the frequency corresponding to this impulse train. And what is that frequency? The period is capital T, therefore the frequency is 2 pi over capital T. So we have k times 2 pi over capital T. They are separated by this much. We also have a notation for this. We call this omega s sampling frequency. K times sampling frequency is the separation or the locations of the impulses. So it essentially looks like this. S of omega is consisting of, again, impulses. It is an impulse train, just like S of t, but its magnitude is 2 pi over capital T, and here we have omega s to omega s, where omega s is equal to, excuse me, where omega s is equal to 2 pi over capital T. Yeah, so this is the omega axis. An interesting thing, impulse train Fourier transform is also an impulse train. The impulse train in time domain is separated by capital T. The impulses in the frequency domain are separated by 2 pi over capital T. So they are inversely proportional to one another. If you make these capital T sampling intervals shorter and shorter, this capital T, then 2 pi over capital T will be larger and larger. And these impulses, the red impulses that you see here, will be very much far away. And in the limiting case, if you can squeeze that capital T all the way down to 0, it makes only a single impulse in the S of omega. S of omega, that will mean that x sub s will be exactly the same as x. So if you can sample with very small intervals, that sampled signal will essentially be the same as the continuous time signal. Because when you convolve with a single impulse, you come up with the same frequency. This is a convolution. And if the right-hand side is a single impulse, it will give you x sub c. Otherwise, it will give you not only x sub c, but its replicas. They will be repeated by a period of omega s. If omega s is too far away, these Fourier transforms shapes of x sub c will repeat at large distances. And that's a good thing, because x sub c may have high frequencies, and if the other replica is too far away, they will not overlap. But if they are very much near, they start overlapping. If omega s is small, which means capital T is large, they start overlapping. And we use a name for that kind of an overlapping situation. Do you remember that from digital signal processing or signal sense systems? When the Fourier transforms overlap, we call it something. Do you remember what we call it? Any answers from you? I'm expecting an answer here. There was a technical name for the overlapping of the Fourier transforms due to convolution with these impulses. When you convolve any shape with an impulse, you make a replica of the shape at the position of the impulse. So with the convolution with the second impulse, we'll make the same shape as a replica, and we will have several replicas. When they overlap, we were using a name for this kind of an overlapping in the frequency domain. Let me draw some. Say it again.
Aliasing.
Say it again.
Aliasing.
Aliasing, yeah, sort of. Yeah, it's correct. I think what you say is correct, but the pronunciation in the correct way is aliasing, actually. But yes, what you mean is, yeah, we were calling it aliasing or aliasing, as many Turks say. Somehow, I don't know why, but Turkish people just say it aliasing for some reason. This aliasing is a name, has which means cover or occlude the correct identity of something. So when you put an alias over the other one, you don't see what's happening beneath. That's what we call aliasing or alias. It's also used as a name. For example, you may be using alias names for logging into Zoom. You may have a name, Işıl Höcek. For example, she may be using an alias with a different name, and I wouldn't understand who that person is. That's what we also call alias. Many popular aliases are just some celebrity names or some well-known names like Spider-Man or things like that. So that's what aliasing is. And here we have aliasing, which is occlusion of the frequency. The typical x sub c of omega shape over the frequency axis. And the easiest thing to draw will be a triangular shape like this. And because of this typical example that we are always using, after some time, students may start thinking that the Fourier transform of real signals are always triangular. That's not correct. I'm just drawing an illustration here. And I am going to say that this is omega c. And because of, let's assume that it's a real signal, because of the conjugate symmetry of xc of omega, it is also from minus omega c. So minus omega c to omega c, we have a value, a peak value, let's notate by a or something like that. And then we are going to convolve x sub c of omega and s of omega. And when we convolve one by one, the impulses will replicate these triangular shapes, okay, the shapes of the Fourier transform of xc of t. I have forgotten to put a 1 over 2 pi here. Although the Fourier transforms are related by convolution, actually there is a scaling factor of 1 over 2 pi. It just comes from signal processing equations. And let us now convolve x sub c of omega and s of omega to obtain, I will draw it on green. So from here and here, I'm convolving to come up with x sub s of omega, which will be this triangle here, which is a convolution of the triangle with the impulse at the center. And the peak value will be a times 2 pi over capital T times 1 over 2 pi, which will give me a over capital T. So the peaks, the top values will be a over capital T. And let's say that this is omega s, and I will have all the other replicas like this. Like this, all right, on the frequency axis. Now, as you see, due to this replications, some overlappings may occur. And this overlapping is what we call aliasing. And it happens when omega c, which is this point, is greater than half of omega s. Happens when omega c is greater than omega s over 2. Or equivalently, omega s is less than 2 omega c. Just writing it, putting it in another way. So in order to avoid such instances, if our signal is band limited, if there is a cutoff frequency of our input signal, then we have to choose the sampling frequency omega s to be less than twice, greater than twice of omega c. So the proper selection requires omega s to be greater than 2 omega c to avoid aliasing, okay? And this proper selection limit is also known as the Nyquist limit, or this limit actually is the Nyquist frequency. So you must sample above the Nyquist frequency or the Nyquist rate, which is twice the highest frequency of the signal, that is omega c. You must sample at more than twice omega c. Now let's assume that, Nyquist rate is obeyed. Then we have x sub s of omega to be equal to isolated frequency slots like this, where omega s, as you see, this one is way larger than twice omega c here. It goes on to the left and to the right on the frequency axis. And the peak value is A over capital T. Or you can also say it like 1 over capital T times whatever the value of omega c, x sub c of omega, this one, was at omega is equal to 0. So you can also write it like xc of 0. Okay? That's the peak value. And it is also periodic with omega s. Now, this thing, this shape that I have drawn, is periodic with omega s. Now, this is the Fourier transform of x sub s of t. So xs of omega is the Fourier transform of x sub s of t. Now, how about capital X of, I have to use a different frequency notation here because I am going to write it as the Fourier transform of, discrete time Fourier transform, of course, of x of n. This is n. According to my book, or the notes that I'm taking from the book, it uses this kind of a notation. So from now on, although I was saying like putting like a lowercase omega everywhere for the Fourier transform parameter, the frequency parameter, as the Fourier transform of t, I am going to use a different notation, and I will draw the same figure as a different omega, because I'm going to use this omega, the lowercase omega, as the Fourier parameter or the frequency parameter for discrete time signals. But this is not a discrete time Fourier transform, it's the continuous time Fourier transform, which we will use very rarely. So I will use something that I will use very rarely, which is xs of, let's say, capital omega. This is also omega, but in a different uppercase Greek letter omega. And let's put these as omega c. Oops, excuse me, just jumped. Omega s. And this is the axis of omega, like this. So omega is the frequency for continuous time signals. Let us notate it like that. Then I will say that x of omega is the discrete time Fourier transform of x of n. And it will be the lowercase omega. So I'm going to use lowercase omega for discrete time signals. The problem is, can we draw capital X of omega on the omega, lowercase omega axis? The discrete time Fourier transform of the discrete signal, discrete time signal. X sub s of t is not a discrete time signal, it is a time signal. The answer from the green shape to the black shape, to the below black shape, is not very difficult. Actually, it's easier than you may expect. You must keep this in your mind. This period of x, or let me say s of t, it's not x actually, the period of s of t was capital T, because that's the period of the impulse train. But on the n axis, we are making every t to be equal to 1. Okay, so I am essentially dividing the time axis. Let me write it. Divide time axis by capital T. So the time axis, when I divide, then the separations will be 1. They will not be capital T. They will be 1. And that is the separation that I expect from discrete time signals. So it's like saying, similarly, n is equal to capital T over, sorry, T over capital T. I'm dividing the time axis by capital T. That's what I'm doing in order to convert the continuous time signal x sub s of t to x of n, the discrete time signal. I'm dividing the time axis by capital T. And conversely, it's like saying the frequency corresponding to the discrete time Fourier transform, the lowercase omega, is like multiplying the frequency in continuous time by capital T. Because if you divide something in time, you have to multiply with the same in frequency. They are inversely related. If you multiply by something in time, then you have to divide in the frequency domain. So this is giving me an impression that I have to have the omega corresponding to capital T times omega. Is it correct? Now let's check it. First of all, this omega s, what was it? It was 2 pi over capital T. The sampling frequency is 2 pi over the sampling period, right? So omega s is equal to capital T times 2 pi over capital T, which is 2 pi. Brilliant. the sampling frequency that I'm going to use as omega s, let me write it as omega s, but I'm going to erase it because it is essentially 2 pi. So I'm erasing it, and I'm going to write 2 pi. So 2 omega s will be 4 pi. 3 omega s will be 6 pi. Minus omega s will be minus 2 pi. How about the rest of the shape? The rest of the shape is just the same. It's the same triangle. Maybe scaled because now the horizontal axis is not periodic with capital omega s, but it is periodic with 2 pi. So you have to scale the horizontal axis correspondingly, but the shapes are the same. Shape-wise, the green and the black signals, Fourier transform signals, of course, they look the same. I'm just converting capital omega s, this one, with 2 pi, this one. I'm just converting these to 2 pi. And I'm claiming that, again, the peak value is A over capital T. This is the Fourier, discrete time Fourier transform of x of n. We must make a final check whether this is an appropriate two-dimensional discrete time, oh, sorry, not two-dimensional, it's appropriate discrete time Fourier transform or not. So the question is, can this be the discrete time Fourier transform of a signal? And for that, you have to check one property. What's that property? It's the 2 pi periodicity of the discrete time Fourier transform. We know that discrete time Fourier transform is 2 pi periodic, a shape, and then at 2 pi it repeats, at 4 pi it repeats, etc. And then look at that. Of course it is. X of omega is 2 pi periodic. So we did it, we made it. Without considering the right-hand side red writings from t to 1 and dividing the time axis by capital T, therefore multiplying the frequency axis by capital T, I could also solve the same problem by trying to make this omega s to be 2 pi, because only then the shape will be 2 pi periodic, which I can call the discrete time Fourier transform. And that would correspond to the same thing. We did the same thing in 2 ways. So it's correct. X of omega is this. But how do we write it? What's the relation between this x of omega, how can I write it in terms of x sub t of omega? How can I say it? First of all, there are infinitely many replicas of x sub c of omega. So I'm trying to relate this to x sub c of omega or x sub c of omega. And the relation between capital omega and uppercase and lowercase omega is that lowercase omega is capital T times uppercase omega. First of all, I can write it like this. X sub omega is equal to 1 over capital T, because there is a scaling factor of 1 over capital T, of x sub c of omega plus 1 over capital T x sub c of omega minus 2 pi over capital T. I'm writing it in the form of capital omega here. So you may find it erroneous or inappropriate, because the left-hand side of the equation is in terms of lowercase omega. The right-hand side of the equation is showing everything in terms of uppercase omega. but I will correct everything to lowercase omega later on. So I can first write it like this, then I can convert everything to lowercase omega by saying that lowercase omega is capital T times uppercase omega, or uppercase omega is lowercase omega divided by capital T. And that's what I'm going to write. 1 over capital T xc of omega over capital T plus 1 over capital T of xc of omega over capital T minus 2 pi over capital T plus 1 over T xc of omega over capital T minus 4 pi over capital T plus etc., which can be combined into a summation form like this. It's a running index of k x c 1 over capital T in parentheses, because both omega and 2 pi's are always divided by capital T, omega minus 2 pi k, like this. Yes, so this is the formula that we have that relates the Fourier transform of the discrete time sample signal x of n to the Fourier transform of the continuous time signal x sub c of t, which is x sub c of omega. If you write it in uppercase omega, it will be 2 lines up. If you write everything in terms of lowercase omega, this will be the sampling. So we are having replicas of scaled version of the original shape. What is the scale? The scale is determined according to capital T. Normally, I should expect x sub c of omega, but it's not x sub c of omega. It is x sub c of omega over capital T. So it is a little bit squeezed or relaxed depending on the value of capital T. So this was a brief review of what sampling is all about. Now, if I use a different capital T and a different signal, clearly it could give me the same x of omega at the left-hand side of the equation. So the underlying continuous time signal is critical for understanding the concept of further upsampling and downsampling, which I will just ask as a or remind you as a question, but I will not continue because we will have to stop. We are running out of time. But what I'm saying is this. Suppose that you have a continuous time signal, okay? And then you sample with capital T and come up with x of n, okay, signal, like this, like the things that we did. And then you apply the so-called downsampling to, let's indicate as x sub 2 of n. Downsampling means the following. You, in the discrete time, you drop every other sample, okay? And you get only x0. You drop x1, you get x2, you drop x3, you get x4. So x0, x2, x4, x6, etc. And then you stack them together and have a signal which is twice shorter than the original one. By downsampling, you reduce the size of the vector, the signal vector. And you do a different operation this time to the same x sub c of t, and then you sample with 2 capital T. and you come up with y of n, a different signal. So your question is, it may be considered as a homework for the next week. If you do this, then the next week's lectures and everything that we will see that will follow will be very easy. But if you don't do this, if you just don't work on it, then you will listen, you will understand something, you will not understand something, but the learning amount will be different. I want you to show that or prove that x of n is equal to, x2 of n, the signal, is the same as y of n. It's very clear, but I want you to prove it by showing that x sub 2 of omega is equal to y of omega. By showing the equalness of the Fourier transforms of the two. How do you do that? You, for one side, for the top branch, you first relate x of n to x sub c of t through the Fourier transform relation that we have. And then you apply the downsampling and you use the downsampling Fourier transform formula in discrete time. You may consult to your DSP books. We will also do this. We haven't done this one yet, but this will be done the next week. So when you do it, you will already know how to do it. To find the Fourier transform of x2 of n and relate it to the Fourier transform of x of n, which is also related to the Fourier transform of x sub c of t. So you will find the relation of, or the formula of capital X sub 2 of omega in terms of x sub c of omega. Okay, so you will relate the Fourier transform of this x sub 2 to the original signal's Fourier transform. And you will also do the same, find the relation between the Fourier transform of y with respect to the Fourier transform of x sub c. So the right-hand side of all these relations will show you that the Fourier transform of y is therefore the same as the Fourier transform of x2. And then you will say that therefore x2 of n is equal to y of n. Otherwise, in the time domain, it's very clear that they are the same. If you sample by t and then downsample by 2, it is equivalent to, of course, it's equivalent to sampling the original continuous time signal by 2t. In fact, we are going to use this relation to find a relation between x2 and y, and then we will also have the relation between x and x sub c. So we will find the relation between x2 related with x sub c. We will also find the relation between x and x sub c. This is already done. It's here. But we will find the relation between x2 and x sub c by finding the relation between y and x sub c, which is equivalent to, this is equivalent to y relation to x sub c. Using this relation and this relation, we will relate x sub 2 to x of n. So x to x sub c and y to x sub c. I have to put this one too. So using these three equations, we will relate x2 to x. What is the relation here? Which we didn't find yet. We will find it. We will discover it. So it will be a two-way verification of the formula for downsampling. First, I will just tell you what it is. Then it will be your exam, take-home exam homework questions or something like that in 2 dimensions to extend this to find the formula for downsampling. The Fourier, what happens to the Fourier transform when you downsample a discrete time signal? Of course, the downsampling rate will not be downsampling by 2, but it will be a downsampling by a matrix M, a 2 by 2 matrix consisting of some numerical, some integer values, including 2s, 1s, minus 1s, etc. And we will see a lot of examples for that. And it's going to be a little bit painful because downsampling is a critical issue. But for discrete or digital systems, it's an issue, and we have to know how to extend it in 2 dimensions. So we will do that. Meanwhile, your question, homework question, which I will not collect, I will not check. It's your own for your goodness to do this. Okay. And then I will stop at this point. Do you have any questions up to this part? I think if you don't have any obvious question, you may come up with some questions once you try to digest all the information that we have. But you may notice some oddities already, and you may ask questions. So I'm waiting for a question still. I'll give you a minute if you have a question. If not, I will stop the recording and the meeting, and we will meet next week. Next week is Tuesday is the Republic Day's Eve, one day before the Republic's Day, which is a holiday. And but before the noon, in the morning time, it's not still a it's not a holiday. Or even if it's a holiday, the eve completely, it may be assigned as holiday, but we are at home, and you are probably at home. You will be maybe, so that you can still join. So what I'm saying is we will do a lecture next week. Okay, that's what I'm saying. Okay, so then I'm stopping at this point. I didn't observe any questions. You may ask by email if you come up with anything as a question. And we will see next week at 9:30 again on Tuesday. So until then, take care. Goodbye.